This is the Building Automation Monthly Podcast with Phil Zito, episode 164. Hey folks, Phil Zito here, and welcome to episode 164 of the Building Automation Monthly Podcast. In this episode, we are going to be talking about relays, switches, and circuits. We've been talking about technology, sales, business development, integration, protocols, etc. for a while now. I think it's time we go back to a topic that is core to our day-to-day tasks in building automation. I was on Facebook the other day and was engaged in a group discussion. This guy was asking about exhaust fans, how to go and turn them on and off, and what to do if you had to have a manual versus automatic control. And it got me realizing that one of the challenging areas for a lot of folks coming into our industry is understanding relays, switches, and circuits. And what are they? How are they interrelated? When do I use what? And what do I need to be aware of? So first off, let's focus in on what a circuit is. So a circuit is just a closed connection, normally closed connection that allows electricity to travel across it. All right. So that's a circuit. When we have a completed circuit, that means from the start point to the end point, there are no breaks in the circuit. Oftentimes we utilize circuits for two main reasons. We have a safety circuit and we have a command circuit. Now, safety circuits, we primarily use them to stop equipment either through programming or directly through interrupting an electrical signal. So oftentimes we will have both a physical circuit and we will have a logical circuit in both of our implementations with our controller. I'm trying to think of how best to word this. Basically, what I'm saying is that you got a controller in the actual software, in the programming, you'll have a logical circuit that is dependent on inputs from physical circuits, and you'll have these physical circuits that will actually break physical signals. So let's kind of talk through this. So if you think about it, you can have both status and control through a circuit, through a safety circuit. So what do I mean by that? Well, status, we will typically have a normally open and a normally closed set of contacts on a safety device. Now, the normally closed set of contacts is where you will typically go and route your control signal through. So if you have a fan command, for example, you may route that fan command through the normally closed on the smoke alarm, through the normally closed on the damper status, through the normally closed on the high and low pressure alarm, and through the normally closed on a low temp. That is the normal safety circuit for an air handling unit or a rooftop unit. Now, on top of that, you have a normally open set of contacts on all of these safeties, typically. And what you'll do is you'll run two wires through those normally open contacts, and that will be your status circuit. So you have a control circuit that I just described running through the normally closed, because as long as nothing's in alarm, that's going to be closed, right? And then on the flip side, you have these normally open circuits, and those are connected to BI's, binary inputs, on your field controllers. Now, what happens is if one of these alarms change state, then not only will it break that fan command circuit, so the fan's going to turn off, but it will also go and send a status to that controller in the logic. Now from there, you can choose to do all sorts of control decisions. You could choose to close dampers or whatever. Typically, that will all be through the control circuit. Typically, you will not depend on the logic in the controller to go and execute safety logic. That'll all be through the physically wired control circuit. But what you'll usually do with those safety statuses is you'll take those will be mapped into the supervisory device, and those will show up as alarms and notifications on a user interface. Now that's your safety circuit. Now you also have things that are known as command circuits, and these are typically used in conjunction with relays. And basically what happens is you have a incoming 24 or 120 volt source that runs through a set of contacts that are typically normally open, and that source then goes to maybe a fan starter or to a heat contactor, and then from that fan starter or heat contactor it goes back to the common. And what that does is that allows a complete voltage circuit to start a fan or to trigger the contactor for electric heat to turn on. So that is known as a command circuit. Now, with command circuits, we are utilizing relays. And the two main types of relays we utilize are command relays for command circuits and status relays for essentially statuses. So why do we use relays? Well, what happens is the command relay. So in order to pull in a large fan starter or heat contactor, that requires amperage. And while some building automation controllers have contacts inside of them that are capable of handling amperage, it's usually a best practice to avoid that. It's a best practice to avoid drawing amps through your controllers. So your controllers tend to cost anywhere from $200 to $1,000, whereas a RIB U1C or an IDEX single pole double throw is going to cost you around $10, so $5 to $10. So you blow a relay, not such a big deal. You blow a $200 controller, it is a big deal. Also, it provides isolation that makes it easier for you to troubleshoot, especially if you're using like RIB U1Cs that have an indicator on them, or even some IDEX that have indicators on them. It shows you whether that relay is triggered or not. Now, what happens with these command relays is that you're going to have this signal, right? You're going to have this signal, and it is going to be going to the relay, and it's going to go from the BAS controller to the coil on the relay. Now, when the coil is energized, the contacts are going to change state. So those normally open contacts are going to close, and the normally closed contacts are going to open. So you've got this electrical signal from this transformer, maybe 120 volts, coming into the normally open contacts and leaving the normally open contacts of that relay. When you turn on your fan command in your building automation controller, that then energizes the coil, which causes that normally open set of contacts to close. And now that completes a circuit which allows that fan starter to turn on, or that electric heat to turn on. And we utilize that for two main reasons. As I mentioned, safety, isolating. So actually, I guess we could say three reasons. We use it for isolating the amperage from our controller. We use it because it's a great indicator that things are actually running. Also, if you do this right and you use a separate transformer, you're isolating your controller from dips in VA draw. So what I mean by that is your controller has certain VA requirements, volt amperes requirements in order to run. Now, typically a transformer will come with something like 100 VA. That's a typical size of a 24 volt transformer. Now what happens is by taking that VA and having a dedicated transformer circuit for your controllers, and then having individual transformers for your control devices, if that control device were to fail and ground out or something and start drawing a lot of amperage, then what that would do is that would go and keep, so you may lose all the control devices, but your controller will still keep running because it is isolated from that now grounded transformer. So it's really important, in my experience, to isolate your commands using relays. I mean, it's super cheap to do, and also use an additional transformer. So that way you go and kind of isolate your power sources as well. Now, we also have status relays. One of the most common status relays is a current sensing relay. And what happens is the current causes the coil to cause the contacts to change state. And then when the contacts change state, that sends a status back to a BI on the physical controller, letting you know that your fan is running. Now, you do have to tune these because they're often detecting amperage across a wire, and you want to make sure that you've got the right amperage, because you can still get amperage if there's no belt and the fan may be spinning, but it may not actually be moving air. So there's a variety of nuances you need to be aware of that we're probably not going to cover in this episode. But the reality is that is one of the most common types of status relays. As I mentioned, we don't want to put the relay inside the controller because we want to go and handle our amperage, our VA draw. We don't want to blow up controllers, and we want to have the ability to understand if our relays are on or off, and that's a quick glance, and it's also easier to troubleshoot with a multimeter. Now, I mentioned switches are going to be covered in this episode, and they're like relays, but they're not. So switches are usually mechanically operated. We often hear of end switches or flow switches, etc. So they don't have a coil that goes and drives their contactors to change state. Normally what will happen, so for example with a flow switch, when it detects flow, it will have a metallic element that gets pushed down and completes a circuit. And now those normally open contacts close, and that BI that is passing typically 5 volts DC through the wire is able to see that that circuit is completed, and now you have fan status. Now the most common switches that we'll see are end switches and contact switches. So end switches are typically on dampers, and we'll utilize those to understand that the damper has closed or has opened rather. And so these come in a variety of different types, but the more common one is that once the damper actuator has fully stroked itself, it will have a end switch built into it, and you can feed your wires through that, or there are actual mechanical end switches that you can attach to the damper assembly itself, and that will give you status of it being fully open. Now, in addition to that, we have contacts. I just described one, the fan status, which is using flow to go and make a metallic element, make contact, and complete a circuit. We also have low temp alarms. Those are contact driven as well. So when the low temp alarm detects that there's a low temp, it will actually go and cause that contact to change state, completing the circuit and taking our normally open loop and making that go normally closed, so that we then have a low temp status. It will also typically have a normally closed loop that will break, and that normally closed loop, when it breaks, is actually going to go and then end up causing that control signal that's passing through to go and be broken. So as I mentioned, we have two main use cases. Those are our status dampers, our fan commands, low temp alarms, things like that. And what you need to know about this is that it's not overly complicated. Relays are pretty straightforward. We have coils and we have contacts. Switches are pretty straightforward. You need to know your normally open and your normally closed side. And on some switches, you may actually have to tune them. So for example, low temp, you have to go and set the actual trip temperature, and then you have to test that it's accurate. The same with pressure switches. You need to actually go and use a magnet helix gauge and a little pump ball and pump up the air to the right pressure to make sure it trips at the right amount of pressure, and you'll go and tune those. Those are all things you'll be doing as a technician. So I hope that this short episode has helped you to better understand and appreciate switches, relays, current sensors, etc. If these are things that are new to you, I really encourage you to look into our Building Automation Fundamentals course. This is just one of the lessons that we cover in the course itself, and it will give you all of that knowledge you need in order to be able to perform your day-to-day job. So with that being said, everything we've discussed is available at buildingautomationmonthly.com/164. And like always, if you have any ideas for future episodes, leave a comment below and let us know what ideas you or topics you would like us to cover in future episodes. Thanks a ton, and take care.